Chemical Equilibrium, Part 5, Calculating KEQ using the R.I.C.E method. Now some people will refer to this as the ICE method, and that's fine too. Before we get into the R.I.C.E method, let's be clear that you can use the equilibrium constant expression to calculate KEQ directly if all of the equilibrium concentrations are known for reactants and products. And that would be the same if you know equilibrium pressures and you're calculating Kp. Here's an example. We have N2 combining with 3 H2s in an equilibrium with 2 NH3s. Now this is happening at 472 degrees Celsius. Remember that KEQ is always going to be temperature dependent. So whenever we're doing any kind of KEQ calculations or dealing with any equilibrium reactions, the temperature should be specified because KEQ will depend on what the temperature is. All right, so let's say that it's given in the problem that the partial pressure of H2 at equilibrium is 7.38 atmospheres. That the partial pressure of N2 at equilibrium is 2.46 atmospheres. And the partial pressure of NH3 at equilibrium is 0.166 atmospheres. What is the Kp, or the equilibrium constant expressed with pressure, at that temperature, 472 degrees Celsius? Well, we know from the balanced equation that Kp can be laid out as the partial pressure of this product raised to the second power divided by the partial pressure of this reactant raised to the first power because there's a 1 coefficient, and the partial pressure of this product reactant raised to the third power because of the 3 coefficient. We can substitute in for PNH3 0.166 atmospheres, or 0.166, and we can drop the units here because Kp will be a unitless value when we're done. So 0.166, remember we have to square that. For the partial pressure of N2, 2.46, that's to the first power. For the partial pressure of H2, 7.38, that's to the third power. Plug and chug that in a calculator and you get 2.78 times 10 to the negative fifth. And again, that would be a unitless value for Kp. Now that's how you do it if you know all of the equilibrium concentrations or the equilibrium pressures. But what if you don't know them all? How do you do calculations for KEQ? Well, first of all, remember that KEQ involves concentrations or pressures for gaseous reactions at equilibrium. So here's how we do the R.I.C.E method. R stands for reaction. We're talking about the balanced equation of the chemical reaction. I stands for the initial concentrations or initial pressures if you're dealing with gases. The change is C, and that's the change in concentrations as we proceed from the initial state to the equilibrium state. And E stands for the equilibrium state or the equilibrium concentrations, pressures if you're dealing with gases, and Kp. And gases can be treated with Kc or Kp, you have that choice if you have all gases. So here's how the R.I.C.E method works. Let's look at an example. Let's say we have a closed system initially containing 1 times 10 to the negative third molar concentration of H2 and 2 times 10 to the negative third molar concentration of I2. And here's our temperature, 448 degrees Celsius. And it is allowed to reach equilibrium, and when that happens, the concentration of HI at equilibrium is 1.87 times 10 to the negative third molar. Calculate Kc, the equilibrium constant for concentrations, at the temperature 448 degrees Celsius. Now, they're giving us the reaction. It's H2 gas plus I2 gas in equilibrium with 2HI gas. They're telling us that the initial concentration of H2 is 1 times 10 to the negative third molar. The initial concentration of I2 is 2 times 10 to the negative third molar. The initial concentration of HI is not given to us. You can look through that and see that the initial concentration of HI is not mentioned. Well, that means that we have to make the assumption that the reaction has not proceeded at all and we're starting out with only reactants and no products. So we have 0 molarity concentration for our product. That's pretty common for products at the start of a reaction to make that assumption that you have zero molarity. So if you don't see that product concentration or product pressure is mentioned here, just assume it's zero and the reaction hasn't started yet. That's the initial condition. Now they also tell us that the concentration at equilibrium for HI is equal to 1.87 times 10 to the negative third molar. That's important. If we know the concentration at equilibrium for one of the chemicals, then we can calculate KEQ. And we do that by using what's called a R.I.C.E table. So here's our reaction. That's our first step. That's R. H2 gas plus I2 gas is in equilibrium with 2HI gas. Notice the mole ratio is 1, 1, and 2. Now that's a mole ratio. The initial conditions are given to us with molarity. 1 times 10 to the negative third molarity for H2, 2 times 10 to the negative third molarity for I2, and 0 molarity for HI. So how is that mole ratio going to help us? Well, let's do this. Let's assume that the volume is constant at 1 liter. 1 mole becomes 1 mole per liter. 1 mole becomes 1 mole per liter, and 2 moles becomes 2 mole per liter. So the mole ratio is also the ratio of concentrations in molarity. All right, well that's nice. So the change in concentration is going to be based on this stoichiometric ratio, 1 to 1 to 2. So we're going to say that between the initial condition and the equilibrium condition, the change that occurs is X amount of that chemical and X amount of that chemical reacts to produce 2X amount of that chemical. Now that can be in molarity or pressure or however you want to do it. It's always going to be 1, 1, 2, X, X, 2X. Now as for the sign, notice that reactants will be diminishing as we progress toward equilibrium. So we'll have negative values here. The change will be negative as the reactant diminishes. That's going to be true for reactions or reactants in reactions always. There'll be negative X values. And for the product, because it's going to increase, that's going to be a positive change. So we have negative X, and positive 2X for our changes. Now, if we sum up the initial condition and the change in conditions, we get the equilibrium condition. So 1 times 10 to the negative third minus X is the equilibrium amount of H2. 2 times 10 to the negative third minus X is equal to the equilibrium amount of I2. And 0 plus 2X, which is just equal to 2X, is the equilibrium amount of HI. Now remember that we were given in the problem that the concentration at equilibrium for HI was 1.87 times 10 to the negative third molarity. So we know that 2X is equal to this. So that's always going to be our starting point here. So let's solve for X. Given that the equilibrium concentration of HI is equal to 2X, and it's also equal to 1.87 times 10 to the negative third, we can say that X is equal to half of that, right? Just divide both sides by 2, and we get 0.935 times 10 to the negative third molarity. That's the value of X. Well, now we know that the equilibrium concentration of H2 is 1 times 10 to the negative third minus X. So 1 times 10 to the negative third minus 0.935 times 10 to the negative third. And that calculates out to be 0.065 times 10 to the negative third molarity. That's the equilibrium concentration of H2. We do the same thing for I2. Plug in the value for X, and we get 1.065 times 10 to the negative third molarity. Remember, this is 2 times 10 to the negative third minus X. So 2 times 10 to the negative third minus 0.935 times 10 to the negative third. Now the equilibrium concentration of HI is 1.87 times 10 to the negative third. So we can plug in the Kc value based on the balanced equation. HI concentration squared divided by H2 concentration divided by I2 concentration. Plug in our numbers. 1.87 squared for HI squared. H2 is 0.065 times 10 to the negative third. So I'm sorry, this is 1.87 times 10 to the negative third squared. 0.065 times 10 to the negative thirds, and for H2. And then for I2, 1.065 times 10 to the negative third. Calculate that all out, and we get 50.51. And again, that's a unitless value. So notice that if we knew the equilibrium concentration of one of the chemicals, we could solve for that X value and go from there. That's how all of these problems are going to work using a R.I.C.E table. All right, so let's do one more example. Sulfur trioxide decomposes at a temperature of 1,000 Kelvin in a sealed container according to this equilibrium reaction. 2SO3 gas is in equilibrium with 2SO2 gas and 1 O2 gas. They tell us that the initial concentration, or rather the initial partial pressure of SO3 is 0.500 atmospheres. The equilibrium partial pressure of SO3 is 0.200 atmospheres. What is Kp at that temperature of 1,000 kelvins? So here's our reaction, our balanced equation. 2 SO3s is in equilibrium with 2 SO2s and 1 O2. Now these are all gases, so we're going to be solving for Kp here. The initial conditions are 0.500 atmospheres for the reactant, and since they told us nothing about the products, we're going to assume that this reaction hasn't started yet and we have no products yet. They might say a minute into the reaction and give us a certain amount of values here, and we could plug those in and that would be fine, but they didn't do that here. So the change in concentration as we go to equilibrium is always expressed based on the stoichiometric ratio. So 2 to 2 to 1. And that's a ratio of moles or molarity, or that could be a ratio of atmospheres too. Remember that the amount of moles is proportional to the pressure. So if it's a 2 to 2 to 1 mole ratio, it's a 2 to 2 to 1 pressure ratio. So minus 2x plus 2x and x. 2 to 2 to 1 for the coefficients, 2x to 2x to 1x for the change that's going to occur. That's always going to be the way the change is laid out. Reactants will always be diminishing, so negative x. Products will always be increasing, so positive x. So negative 2x, positive 2x, positive 2x. Reactant, product, product. All right, so then if we combine or sum up the initial conditions and the change, we get the equilibrium conditions. So 0.500 minus 2x is equal to 0.200 atmospheres. That was given to us. Remember, we have to know the equilibrium condition of one of the chemicals. This is going to allow us to solve for x. We know that 0 plus 2x is 2x and 0 plus x is x. All right, so let's go here and solve for the x value using this equality. 0.500 minus 2x is equal to 0.200. Minus 2x is equal to 0.200 minus 0.500. We just subtracted 0.500 from both sides. And it turns out to be equal to negative 0.300. Divide both sides by negative 2, and x is negative 0.300 minus, or rather, divided by negative 2, and that's equal to 0.150. Now, we know that Kp can be put together based on the balanced equation. So, the partial pressure of this chemical squared times the partial pressure of this chemical to the first power, because there's a coefficient of 1, divided by the partial pressure of this chemical squared. And that's equal to, at equilibrium, 2x squared multiplied by x, right? Because this would be 2x, and we have to square that. This would be x. And then the partial pressure of SO3 at equilibrium is 0.2. So we have to square that 0.2 value. So let's plug in our numbers. 2 times x is 0.150 squared multiplied by 0.150 divided by 0.200 squared. Plug that in your calculator, and be careful that you plug that in appropriately, and you get 0.338 as our unitless value for Kp.